Hello, I am Zegam. On behalf of my team comprising of researchers from ETRI, UST, ITU, MBZUAI, and ETH Zurich, I would like to introduce our work, Generative Cooperative Learning for Unsupervised Video Anomaly Detection. Anomalies are subjective and often location dependent. Also, unlike other datasets in the domain of object detection or classification, it is not easy to obtain particular anomaly examples. Therefore, it is feasible to have approaches that can train on the data recorded at certain locations without needing precise annotations. Several researchers proposed one-class classification networks in which the classification boundary is learned using only normal data. Some OCC methods claim to be unsupervised. However, as clean normal data is needed, OCC is not really unsupervised. Another protocol for anomaly detection is to utilize both normal and anomalous examples for training in a weakly supervised setting. In this setting, video level annotations are provided to train a frame level anomaly predictor. What if we go completely unsupervised? Surveillance videos have a lot of characteristic attributes such as abundance of data, richness in information, rarity of anomalies, and unique anomaly properties such as rapid changes, fast local motion, and so on. However, the question is it possible to utilize these attributes to train anomaly detectors without any labeling? So, the goal is to train an approach capable of taking long sequences of unlabeled videos and predicting frame-level anomaly scores. However, this task is highly challenging and conventional approaches like a standalone autoencoder will not provide any benefit. In order to solve this challenging problem, we propose a collaborative learning approach. First, the training data organization is explained. All input videos are converted into features and transformed into batches. Then, for our generative cooperative learning, two learning models are used, including a generator and a discriminator. Each model is used to generate pseudo-labels for the other model to train on. Therefore, the loss of a given model is computed based on the pseudo-labels generated from the other model on a given input batch. More precisely, the generator is trained to minimize the reconstruction loss of the input feature vectors. Each feature vector scoring higher than a certain threshold is pseudo-labeled as anomalous. Then, the discriminator is trained to minimize the binary cross-entropy loss for the input feature vectors using the pseudo-labels created by the generator. Afterwards, the pseudo-labels from the discriminator are created using a specified threshold. We also utilize negative learning for generator to better discriminate the reconstructions of normal and anomalous input features. Precisely, for a given input batch, pseudo-labels are created from the discriminator. Then, for each feature vector pseudo-labeled as anomalous, the generator is encouraged to not reconstruct it properly by providing it with a pseudo-reconstruction target. Two large-scale surveillance datasets, UCF Crime and Shanghai Tech, have been used to evaluate our approach. Score distribution visualizations can be seen here, comparing a naive autoencoder with the two components of our approach. Our approach demonstrates significantly improved discrimination between the anomalies and the normal data. A detailed AUC comparison of variants of our approach is provided under one-class classification, weakly supervised and unsupervised settings. As seen, our approach outperforms most compared methods in all three categories. We also evaluated different variants of negative learning. Although the overall performance of these techniques is comparable, one's negative learning is the most stable and effective. A TSNE diagram plotting reconstructions of the input features also demonstrates that with negative learning, the reconstructions of the anomalous inputs marked as red dots start to successfully isolate from the reconstructions of the normal features. Score evolution and some qualitative scores predicted by our approach are shown here. Anomalous portions are accurately predicted in most cases. Unsurprisingly, by adding supervision, even though it is just weak video level supervision, the performance of the overall system increases. Moreover, it is interesting to see how an addition of 33% weak labels can improve the performance significantly from 68.17% to 74.81%. In conclusion, to the best of our knowledge, this is the first rigorous attempt to address unsupervised video anomaly detection. We propose a simple cooperative learning framework which is evaluated on two large-scale datasets. Thank you very much for listening.